Good morning, my name is Kira Proctor and I'm the Managing Director of the A. Proctor Group Limited. And welcome to this morning's webinar, a 35-minute RIBA assessed look at the pitch roofing design considerations relating to energy, moisture and air permeability. We'll be following on the CPD with our regular live Q&A session beginning at about 10:35. This presentation will look at the pitched roofing design and what strategies we can adopt to manage the movement of air and moisture to ensure our roofs are both energy efficient and free from condensation. We'll start out with a look at the relevant legislation and guidance, including BS 5250/2021, the Code of Practice for Moisture Management, how it relates to roof design and the building regulations, and some of the roof types it introduces. We'll then look at the physics and design influences in more detail and how roofing practice is adapting to meet the changing nature of these challenges. Let's begin by considering moisture management. In the UK and Ireland, the management of moisture associated with roof space condensation in buildings is considered in Approved Document C for England and Wales, Technical Handbook Section 3 in Scotland, and Technical Guidance Document F in the Republic of Ireland. Northern Ireland is also Part C, but this is a different document from the one used in England and Wales. Whilst these four documents each have a slightly different focus and approach when it comes to construction moisture control, they all refer designs to the same Code of Practice document, the British Standard BS 5250. Building on the 2017 BSI White Paper, Moisture in Buildings, an Integrated Approach to Risk Assessment and Guidance, BS 5250/2021 takes a more holistic view of the effects of moisture on buildings and the strategies for its management. This reflects an increased understanding of the interlinked nature of hygrothermal effects. From here, we can consider the factors influencing design in greater detail. Vapour drive through the roof structure. This is influenced by the internal and external environmental conditions present on the specific project. In the UK and other heating climates where buildings are heated more often than cooled, this will typically be from inside to outside. The level of vapour drive is determined by the building type, use and occupancy. A large, cool, low-occupancy building, such as a warehouse, will have a low vapour load, which something like a swimming pool, which is typically more warmer and humid, will have a correspondingly higher moisture load. Off-site construction, such as timber frame or SIP buildings, will also tend to have lower moisture loads, as there are less wet trays to dry out, and the building is usually wind and watertight earlier in the construction process. The construction moisture can lead to significantly higher condensation risks in the short term after completion. The vapour drive present determines the overall condensation risk that will be present, and as such is the start point of the hygrothermal assessment of the roof's performance. Should subsequent repair or upgrade work, such as adding MVHR or a change of use for the building, have the potential to affect the indoor environment, the performance of the roof systems should be reassessed to account for this. Airtightness of the roof. The airtightness of the overall roof construction, as well as the individual components, is also an important influencing factor. Whilst the vapour drive present in a project establishes the question of what condensation risk is present, the air leakage rates involved begin to shape the best answer. If the energy performance assessed in the Home Energies Model, or SBEM calculations, require a low air leakage rate, that may influence the choice of roof construction or the components specified, as some types of roofs can achieve lower air leakage rates more easily, particularly if extremely low air leakage rates such as those found in passive homes is required. Ensuring the transfer of warmer, more humid internal air is limited, it is also important as air leakage can transfer moisture directly into colder areas, leading to localised condensation. Similarly, the air permeability of the outer covering must be considered, as roofs with continuous coverings such as metal sheets or photovoltaic panels will have a significantly different hygrothermal performance from discontinuous roof coverings, such as tiles or slates. Insulation specification. The dew point temperature associated with roof design is the point at which the warm, moist internal air cools sufficiently to lose its ability to carry moisture. This is the point at which liquid condensation will form. The location of the dew point within the roof structure is therefore a critical factor in assessing the performance of the roof. As this is influenced by both the temperature gradient and the vapour drive, the specification of the insulation has a significant effect. As the level of thermal insulation increases, the outer layers of the roof will become colder with correspondingly higher condensation risk, all else being equal. Conversely, a more vapour-resistant insulation will limit the quality of moisture, which is able to reach these colder areas, lowering the risk. Achieving a good understanding of the hygrothermal performance of the insulation is important, as part of the role of construction membranes in roofing is to help balance these characteristics, limiting the risk of harmful moisture issues. Without good information and solid specifications for the thermal envelope, ensuring vapour control layers and underlays with the correct performance characteristics are chosen for the project can be difficult. If insulation levels are altered during the building's life, either as part of repair works to improve the energy performance, then the effects on balance of the roof system as a whole must be reconsidered. Wind washing describes the process of weather-driven airflow inducing additional heat transfer through the insulation layers. In extreme cases, this airflow can also affect the dew points by moving colder air further inwards. Although this issue is more prevalent with permeable fibrous insulation, it's worth bearing in mind that simply friction fitting rigid vapour and airtight insulation boards between structural members may not be convection tight. If the joints and interfaces around rigid boards are not sealed and tolerances tightly controlled, there may still be gaps allowing both wind washing and convection-driven airflow around the board, reducing thermal performance and introducing additional moisture loads which may not be accounted for in the hygrothermal design. A successful roof design must, of course, provide weather protection, and this is true not just throughout the life of the building, but also during construction. The outer roof covering must be able to resist extremes of weathers is an obvious consideration, but in such extreme conditions, the performance of the secondary weather protection measures is also important. In the event of storm damage to tiles, slates, or ridge tiles, having a robust and durable secondary layer to protect the roof until repairs are completed can be the difference between a relatively simple and limited repair, and something far more disruptive to the building's occupants. Another aspect to consider regarding weather protection is how wind-driven rain or even snow can enter a roof structure. Roof ventilation, if specified, should have openings carefully designed and positioned such that rain and snow cannot enter the roof space or saturate insulation and roof timbers. Ensuring all parts of the roof structure can properly resist wind loads without damage is also important. As with many aspects of roof design, this may have a knock-on effect to other parts of the specification. For example, if a particularly exposed location requires the use of additional wind bracing or sarking boards, or necessitates changes to the specified outer covering, this may require additional or different condensation control measures. Escape of moisture. As well as preventing the ingress of moisture from external sources, a properly designed roof system must enable internal moisture to escape and the building as a whole to dry out. This not only means ensuring condensation problems are mitigated, but it is also important in ensuring acceptable indoor air quality is maintained. This necessitates a good understanding of the hygrothermal properties of every layer from inside to outside, and ensuring specifications which are designed and modelled remain fixed through to completion. There can be substantial differences in the performance of seemingly similar materials which product literature and different test methods do not always make obvious. While CE marking in the Construction Products Directive went some way to clarifying and standardising testing and the presentation of information, third-party certifications specific to the proposed application remains the most effective way to ensure design criteria are met. This is particularly important during the transition from CE to UKCA. Whether or not roofs and lofts require ventilation has been the subject of a long-running but now largely settled debate across the industry since vapor-permeable underlays first gained mainstream acceptance in the 1990s. BS 5250/2021 does not address situations where ventilation is omitted, but in section 12.5.3 refers designers to UCAS or equivalent, accredited third-party technical approvals, for guidance where non-ventilated approach is taken. We'll come back to this later in the presentation. Traditionally, roofs of all kinds required ventilation to ensure moisture could escape, as bitumen felt underlays did not allow moisture transfer to any significant extent. Whilst there's nothing wrong with this approach and it's been used successfully for a very long time, as buildings become increasingly well sealed and moisture loadings increase, it's not always optimal. This is particularly the case where complex roof shapes and rooms in the roof are present, creating the potential for dead spots where air cannot properly circulate, leading to localised damp and mould. BS 5250/2021 gives prescriptive guidance on how best to design ventilation to avoid these problems. Ensuring these areas are adequately ventilated is important in reducing remedial action, as the retrofitting of additional ventilation to resolve issues can involve complex work at height, which may impact on CDM regulations and considerations. If not carefully designed, the pressure drop between a ventilated loft, particularly if ventilated at the ridge only, can set up additional suction forces on the ceiling, drawing both heat and moisture from the habitable spaces below. Any changes to the ceiling assembly, for example adding downlighters, or in the longer term, maintenance to building services such as HVAC systems, may affect how this moisture can enter the roof space. The impact of any proposed alterations or maintenance work on the airtightness of the ceiling assembly should therefore be fully considered at the earliest possible stage. Finally, vents may be inadvertently blocked by stored items in the loft, or purposefully blocked by homeowners who may not fully appreciate the importance of this airflow, choosing instead to block up the drafts to warm the loft up. Any subsequent loft conversion may be complicated by the need to maintain good airflow. Adopting a fail-safe approach to moisture management reduces the potential for long-term problems to arise in the roof construction, either as a result of upgrade or conversions work or arising from repairs and maintenance. If insulation levels are increased as part of energy performance-related upgrade work, this can also block the ventilation openings at the eaves, or if it stops short of the wall insulation, lead to a cold bridge at the wall-roof junction. Either way, this can result in elevated condensation risk and attendant moisture problems. In addition to the hygrothermal design criteria outlined in BS 5250/2021, it's also important to understand the performance of the roof assembly in relation to fire. In roofs, the primary requirement outlined in Approved Document B is to limit the spread of fire both from an external ignition source and between adjoining roofs. A roof is designed in Approved Document B as being less than 70 degrees from the horizontal. Above 70 degrees is considered a wall. AD-B Clause 11.14 acknowledges there is a matter of judgment about whether features such as large runs of dormer windows should be counted as wall sections. Internally, Requirement B3 applies, requiring subdivision of fire-resisting construction between adjoining buildings, and this should extend into the roof space. Such subdivisions should be treated no differently than any other compartment wall. Depending on the building type, ADB2 may require additional separation between parts of a single building with different functions. Again, this requirement extends to the roof spaces above these areas. B3 Clause 4 also requires measures to be taken to limit the unseen spread of fire and smoke within concealed spaces. And Section 8 and 9 of ADB1, 9 and 10 of ADB2 detail the provisions that should be made to ensure cavities and openings are adequately fire stopped, for example with cavity barriers or other proprietary systems. Externally, Requirement B4 requires the walls and roof to resist fire spread over the element and between buildings. Although Regulation 7, Paragraph 2 states that materials used in external walls should be of European classification A2-S1D0 or A1, classified in accordance with the reaction to fire classification, Paragraph 3 exempts most roofs from this requirement. Regulation 7, Paragraph 3 also provides an exemption for membranes such as roof underlays. So from a thorough understanding of these high-level factors influencing the building performance, we can then consider the fundamental interaction of heat, air and moisture movement through the fabric of the structure. BS 5250/2021 gives definitions for various terms related to the management of moisture. This includes definitions and performance criteria for the most commonly used type of construction membranes. AVCL, or air and vapor control layer membranes, are used on the warm side of the insulation to limit the ingress of moisture into the construction by both diffusion and by convection, air movement. DPM or damp-proof membranes are used at ground level to prevent the ingress of ground moisture into the structure. There is a requirement to provide gas protection, for example on brownfield sites, and then some DPM membranes can also work as barriers to gas and other on-site contaminants, although these types of membrane are out with the scope of BS 5250. HR roof underlays are traditional roofing felt and modern plastic equivalents, which provide secondary weatherproofing on roofs and are effectively impermeable to all forms of moisture. Roofs using HR membranes will always require some form of ventilation to be provided. LR roof underlays also provide temporary weather protection, but are also permeable to moisture vapour, which may allow the ventilation requirements to be reduced. Some LR underlays are air permeable as well as vapour permeable, and we'll discuss the effect of this later in the CPD. Finally, vapor permeable membranes fulfill a similar function to LR underlays, but in walls and metal sheet constructions. These used to be commonly referred to as breather membranes, as the passage of moisture vapor makes it breathable. Whilst they perform a similar function to LR underlays, the performance requirements are different and less onerous in walls. So while some LR underlays can be used on walls as VPMs, and vice versa, the two membrane types are not interchangeable, so care should be taken in specifying the right material for the application. BS 5250/2021 defines 4 classes of pitched roof constructions, with a pitched roof being a roof over 10 degrees of pitch, but less than 75 degrees. There's also definitions included for other types of roofs, along with walls and floors, but for today we're focusing on pitched roofing. Cold pitched roofs. In this type of roof, the insulation is placed horizontally across the ceiling ties, with the loft space and the structure of the roof being out with the building's heated envelope, hence cold. This type of roof typically uses fibrous quilt insulation, which is both air and vapor permeable. Warm pitched roofs. In this roof type, the insulation follows the pitch of the roof, either between the structural members, over the top of the structure, or a combination of both. This leaves the enclosed space under the pitch as part of the heated envelope. In warm pitched roofs, it's more common to see the use of rigid foam insulation, which tends to be more vapor and airtight than fibre insulation. This is primarily due to the thickness of insulation required to meet thermal standards, however, and there's no fundamental reason permeable insulation types cannot be used. Hybrid pitched roof. In this type of roof, most commonly found where there is a room in the roof, such as in loft conversions, has a mix of horizontal, vertical and inclined insulation. This means some parts are cold roofs and some are warm, with a corresponding mixture of insulation types commonly used. It's also worth noting here that the term hybrid warm roof is sometimes used to describe a roof with insulation positioned both between and over the roof structure. Structural insulated panel, SIP roof. SIP roofs use panels which combine the supporting structure and insulation layers into a single panel. Typically, these panels are comprised of a rigid foam insulation and timber sheeting like OSB or plywood. All these component parts are relatively air and vapor tight. For each of these roof types, the only prescriptive guidance in BS 5250 for removing moisture from internal sources is by means of providing ventilation. This means providing ventilation openings at the eaves and/or ridge of the roof, and using the resultant airflow to remove moisture. In a cold roof, this means that air must circulate through the large loft void to remove warm, moisture-laden air and prevent condensation occurring on the colder surface of the underlay and roof timbers. With an impermeable HR underlay, cold roofs like the one shown between 15 and 75 degrees will require 10,000 millimeters squared or opening per meter length at the eaves, and an additional 5,000 millimeters squared per meter at the ridge if the roof span exceeds 10 meters. The pitch is over 35 degrees or the roof is a monopitch. Below 15 degrees, 25,000 millimeters square per meter is required at the eaves. With a permeable LR type underlay, the eaves ventilation can be reduced to 7,000 millimeters square per meter or 3,000 millimeters square per meter if the ceiling is well sealed, as defined in BS 9250. In warm roofs, the risk of condensation problems is typically lower as there's no large void present for moisture to accumulate. But if an HR underlay is used, ventilation must still be provided. A ventilated void of at least 25 mm should be provided between the insulation and the underlay, taking into account any drape in the underlay. Ventilation openings into this void should also be provided, 25,000 mm squared per meter at the eaves and a further 5,000 mm squared per meter at the ridge. Voids and openings should be arranged such that ventilation airflow can pass across the entire roof, taking into account any obstructions like dormers or fire break walls that are present. So in practice, additional ventilation openings like slate tile vents may be needed to ensure this. For walls with type LR underlays, ventilation can usually be omitted provided the outer covering of the roof is air permeable. We'll look into air permeability of both underlays and outer coverings in more detail later in the CPD. Last type of pitched roof which BS 5250 gives prescriptive guidance is room in the roof. This type of roof has a mix of warm and cold sections, with large voids present at the eaves and ridge. The ventilation requirements for each section of this type of roof are the same as for roofs which are entirely warm or cold, but care must be taken at the junctions. Where a roof transitions from cold to warm and vice versa, it's important to ensure the air can move between the various areas uninhibited, which can make detailing both ventilation and the position of AVCL membranes challenging. This is especially the case where dormers, complex roof shapes, and subdividing walls are present. Another potential issue to consider is the continuity of the insulation layer and the potential for cold spots to form internally. At such locations, moisture vapour can condense internally, causing localised surface condensation and, in extreme cases, mould growth. Similarly, air movement through the fabric of the roof can transport moisture vapour into colder areas, where it can form condensation. Again, this highlights the interlinked nature of heat, air and moisture control in buildings. What if we could do away with ventilation altogether? This would introduce a number of benefits. Firstly, moisture vapour could escape through the entire surface of the roof rather than specific inlets and outlets. This simplifies the design of complex roof shapes and makes obstructing or inhibiting the flow of moisture out of the roof virtually impossible. Secondly, if there are no openings in the roof, there's no possibility of wind-blown rain or snow entering the roof through poorly designed or installed openings. Lastly, the latest 2023 amendments to Approved Document L require a significant increase in the depth of loft insulation, which makes the detailing of the eaves problematic. If the insulation does not extend a sufficient distance into the eaves, it can introduce a cold bridge at the junction with the walls. However, if it's pushed in too tightly, it can obstruct the openings for ventilation. This means additional measures such as plastic trays or ventilators must be used to ensure airflow is maintained. Where an airtight LR underlay is specified on the roof, the BS 5250 standard does not directly address situations where ventilation is either reduced below the levels given in section 12.5.4.1, table 5, or eliminated altogether. However, if the underlay membrane is covered by appropriate third-party certification, it may be permissible. In this case, it is assumed that the vapour derived from the heated space alone is sufficient to drive moisture out of the roof space. In practice, however, membranes of this type can struggle to deal with the elevated vapour loadings during the drying out period, which may require the temporary use of dehumidifiers in the building in extreme cases. One method of addressing this is additional initial moisture load, and that adopted by the NHBC in Technical Standard 7.2.15 is to introduce additional ventilation at the ridge only, equivalent to 5 mm squared by the longest horizontal dimension of the roof. This must be used in conjunction with a well-sealed ceiling construction, as defined in BS 9250/2007, Code of Practice for Design of the Airtightness of Ceilings and Pitched Roofs. It's not clear, however, how effective this type of ventilation is, given no airflow into the loft is possible through the well-sealed ceiling assembly or the airtight underlay. It's also important to bear in mind that whilst it might seem like all LR underlays are interchangeable, this is often not the case, and the third-party certification for each membrane can include some important differences. A good example of this is when we consider the air permeability of membranes. While specific guidance regarding air permeability was included in the initial drafts of the 2020 BS 5250, it was latterly removed, leaving these important additional considerations to be dealt with via third-party certification only. The final 5250/2021 text simply includes the following footnote. Most LR underlays are airtight. However, some are designed to be air permeable. This property can allow air movement from the loft space through the underlay into the batten space, thereby reducing the risk of condensation on the underlay and cold structure. Air permeable or air open underlays provide, in the opinion of the BBA, a significant additional mechanism for water vapour egress by convection, and therefore sometimes have less restrictions on their use. For example, some air-open membranes may not require the use of a well-sealed ceiling or vapour control layer. The requirements might vary between the membranes though, so it's important designers and installers are aware of these differences. Whilst it may seem that one type LR membrane can simply be swapped for another, and indeed this may arguably be true of airtight LR underlays where ventilation is used, for completely non-ventilated constructions the picture is more complex. Not all membranes are the same, particularly where an air-open underlay is specified. So how do we define whether a membrane is air permeable or not? Again, the helpful common definition in the BS 5250 drafts has been removed, leaving a more complex picture. There are currently two definitions commonly used, one given in BS 5534/2014 and A2/2018, and another used by the NHBC outlined in Technical Extra 24 November 2018. BS 5534 gives the figure of not less than 20 metres cubed per square metre per hour at 50 PA, but this is primarily intended for when considering wind uplift on tile assemblies and may not provide sufficient airflow to adequately reduce condensation risks as is intended in the BBA's guidance. The NHBC takes this position and therefore uses a higher figure of 34 metres cubed per square metre per hour at 50 PA or more, as the minimum necessary to provide the ventilation effects required to minimise condensation. Both use the same EN 12114 test method, however, which simplifies matters. As is the case with vapor permeability, ensuring the test data is directly comparable is important. As well as the air permeability of the underlay, it's important to consider the air permeability of the other parts of the roof system. If the outer covering is not sufficiently permeable to disperse moisture vapor exiting the roof structure through the surface of the underlay, then this must be addressed. The standard for air permeability of the outer roof covering used in BS 5250-2021 is defined in the BS 5534-2014 and A2 2018 standards as follows. The air permeability of an outer weatherproofing covering comprising discontinuous units may be determined by testing in accordance with BS 5534-2014 and A2 2018 Annex L, using equipment capable of measuring pressure differences of 10 Pa. The outer weatherproof covering is deemed to allow sufficient air movement and be air permeable if the airflow in meters cubed per hour at differential of 10 Pa is greater than 17.4 AR, where AR is the area of the outer weatherproof covering under test in meters square, as defined in 5534-2014 and A2 2018. If the airflow is not greater than 17.4 AR in meters cubed per hour, then the outer weatherproof covering is deemed air impermeable. If it's not permeable, then some degree of ventilation will be required. In most cases, this requirement to ventilate will apply to coverings such as metal sheeting or roofs fitted with photovoltaic panels, as slates and tiles usually offer sufficient air permeability. If the roof covering is later replaced as part of repair or upgrade work, any changes that may affect its air permeability should be taken into account. This is particularly relevant where photovoltaics are added to an existing building. Once again, reference to third-party certification is important to ensure the entire roof system functions effectively and all systems specified are working well together. If ventilation is required, this typically consists of a ventilated batten and counter-batten space directly below the outer covering. This is a separate consideration from ventilation of, for example, the loft space, although if the loft space is ventilated, it's usually not necessary to ventilate the batten space too. In some specific situations, such as where wind loads may be particularly high, or where traditional Scottish slating practice is being used, there may be sarky materials present on the roof. In such cases, it's always a good idea to check what the effect the specific sarking type has on the ventilation requirements for the roof, particularly if reduced or no ventilation is proposed. BS 5534-2014 and A2 2018 also discusses wind forces acting on a roof and gives methodologies for calculating these. On the windward side of the roof, this force pushes downwards. On the leeward side, the force acts upwards. This suction force acts on both the outer covering and on the underlay, with the proportion of the force on each determined by the air permeability of the outer covering and of the underlay. If these wind forces are not properly accounted for, including the effects and influence of both the specific outer covering and the specific underlay, then this may result in damage to the roof. Finally, we must consider the effects of the roof design and configuration on the air tightness of the building. The level of air leakage can have a significant effect on the overall energy use. Air tightness is addressed in the sections of building regulations relating to energy performance. This means approved documents L in England and Wales, Technical Standard 6 in Scotland, Technical Booklet F in Northern Ireland, and Guidance Document L in the Republic of Ireland. In most of these cases, the energy performance requirements can be slightly different across the regulations and also vary with building use. Where an air-permeable LR underlay clearly presents the most effective solutions to ensuring moisture can escape from a roof structure, this does make the sealing of an internal air barrier, be it an air and vapour control membrane or a well-sealed ceiling, of considerable importance. Whilst it may be tempting to consider an airtight LR underlay as a good step to reducing air leakage, such membranes will often require a degree of ventilation, such as the ridge-only openings. In practice, this means an airtight underlay does not necessarily mean an airtight cold roof. If the ceiling or air barrier requirements are more or less the same either way, a vapour-permeable membrane which is also air-permeable presents a far simpler, more reliable and fail-safe means of ensuring condensation risks are mitigated in cold and hybrid roof applications. This type of construction is also better able to accommodate future changes such as increased insulation thickness without requiring revisions to the ventilation, vapour control or air leakage design. Given the various categories and differing guidance for ventilation and the lack of clear specification advice for more complex roof types and shapes, a similar option is often to omit the ventilation altogether and rely instead on the vapour permeability of the underlay to remove moisture. Construction Design and Management Regulations 2015 set out the duties placed on designers, and these must be referenced by both the architect specifying the system and the product manufacturer and installer who are designing the system. Responsibilities include the duty to eliminate, reduce, or control foreseeable health and safety risks through the design process, such as those that may arrive during construction work or in maintaining and using the building once built. CDM 2015. The CDM framework aims to improve the health and safety in the industry by helping to sensibly plan the work so the risks involved are managed from start to finish, have the right people for the right job at the right time, cooperate and coordinate your work with others, have the right information about the risks and how they are being managed, communicate this information effectively to those who need to know, consult and engage with workers about the risks and how they are being managed. The faster and simpler installation inherent in reducing or removing the ventilation requirements reduces the need for work at height and for communicating detailed specification guidance to contractors, especially where multiple different roof designs may be present in a development. It also simplifies the overall design, thus requiring less ventilation and oversight of the installation. A more fundamental consideration is the general suitability of cold roof constructions in buildings where air tightness and energy use are the primary focus, such as passive and low energy homes. Roof specification can have a major effect on the overall heat loss from a building, but increasing thermal insulation levels and reduced air leakage must be accounted for in the hygrothermal design. We must also consider the performance gap between as designed and as built performance. Warm roofs, particularly those constructed off-site, typically simplify meeting these goals reliably on-site, but there are other environmental factors to consider. Ensuring the roof can accommodate upgraded thicknesses of insulation in future helps future-proof the roof against unintended consequences of such upgrades. Similarly, the recyclability of products and systems should be considered. There's often a balance to be struck between technical in-service performance and end-of-life disposal. For example, the environmental impact of plastic-based membranes may be offset over the life of the building by the reduced heat loss or more durable building envelope they facilitate. In most cases, all types of roofing underlay is heavily punctured with a variety of fixings during installation, so such systems are unlikely to be suitable for reuse once installed. Polypropylene, which is a commonly used material for roofing underlays, is an easy, recyclable type of plastic. Such plastics are also less hazardous and potentially polluting as waste material than bitumen-based underlays. Some commonly used materials, particularly traditional felts and some types of roof covering, may require specialist disposal during demolition to be safely reused or recycled. Manufacturers' environmental product declarations, where available, should be consulted to provide insight into the embodied energy and carbon of specific products. They can also provide important information regarding the recyclability of the material. In the context of pitched roofing in the UK, EPDs can play a valuable role in promoting sustainability and guiding decision-making in roof construction and maintenance. EPDs provide detailed information about the environmental performance of roofing materials, including their carbon footprint, energy consumption, resource use, and emissions. Building owners, architects, and contractors can use this information to compare different materials and make informed decisions based on their environmental impact. EPDs can provide the necessary documentation to demonstrate the contributions specification decisions can make towards achieving specific sustainability goals and help quantify environmental impacts. They can also provide useful insights towards life cycle assessments of structures, evaluating environmental impacts from raw material extraction and manufacturing to use, maintenance and disposal of the systems and components used. Another context in which we should consider sustainability is in terms of maintenance over the long term. The UK experiences a variety of weather conditions throughout the year, including rain, wind, snow, and fluctuating temperatures. These elements can cause wear and tear on roofing materials over time, leading to leaks, cracks, and damaged shingles or tiles. The damp climate in the UK creates ideal conditions for moss, algae, and lichen to grow on roofs. Not only does this affect the appearance of the roof, but can also cause damage to the roofing materials if left untreated. Gutters play a crucial role in directing water away from the roof and foundation of the building. However, they can become clogged with leaves, debris, and moss, leading to water pooling on the roof and potential water damage. Flashing is used to seal joints and prevent water from seeping into vulnerable areas of the roof, such as around chimneys, vents, and skylights. Over time, flashing can deteriorate, leading to leaks and water damage. To address these issues and ensure the longevity of the roof system, it's essential to schedule regular inspections and maintenance by qualified roofing professionals. This includes cleaning gutters, removing moss and debris, repairing damaged shingles or tiles, and addressing any structural or flashing issues as needed. Additionally, investing in high-quality roofing materials and ensuring proper installation can help minimise maintenance requirements and prolong the life of the roof. That concludes today's presentation, and we'll now move on to the Q&A session. Good morning, everyone. Thank you very much for attending our third webinar of 2024. With more than 125,000 views to date of our webinars, we hope that this continues to grow. We also have some additional news this month that we have launched our very own Proctor podcast. It's called All Things Construction. So the first episode of the Proctor podcast delves into the world of modular construction, and this can be accessed via our website, and you can find it on Apple, Spotify, and various other platforms. I'd be really interested in any feedback you have on that if you have time to have a look. So if you've attended our webinars before, you'll know that we will try our best to answer all your questions. So please ask them either right here on YouTube, email us at webinar@proctorgroup.com, or message us on our social media platforms. We've got quite a few on YouTube already. It's looking very busy, and I've got a number via email as well. So we'll stay on as long as we can to get these answered for you. If you'd like to request some product information, you can now do that on our webinar page, or book a meeting with our staff, ask technical questions, etc. I saw a question earlier on the YouTube feed, and personalised CPD certification is also available at the same link. The next webinar, normally I have a date for your diary. I don't have that at the moment because we're still working hard on our next webinar. So that will be announced on our website in the coming weeks. So please keep an eye out for that. It really helps us if you've enjoyed the webinar to give us a thumbs up. And if you subscribe to our channel, you'll continue to get any updates about what we have coming in the future. So I'd just like to introduce the panel. If I can start with Ian Fernington, who's our Technical Director. Morning, Ian.
Morning, Kira.
And we have Will Jones, Head of Business Development. Morning, Will.
Morning, Kira. Morning, everyone.
And another very familiar face, Pamela Howitt, who's our Senior Technical Advisor.
Morning, Kira. Morning, everyone.
And last but not least, our Technical Regional Sales Manager, Mark Blackie.
Morning, Kira. Good morning, everyone. Good
morning. Okay, so goodness me, plenty of questions. So please bear with me because they come through on Twitter, YouTube, and email. So I'll try and get them. If I miss any, then I apologize in advance, and we will email you afterwards. Okay, so I'll just begin with one that we've had, first of all, here from Matt. So Matt, you've obviously asked a question around some issues with condensation. Our partnership with Roof Shield actually ended last year, and so that's not something we can comment on. However, if you email technical@proctorgroup.com, we can provide you with information and contact details for the manufacturer, who will hopefully be able to help you out with your question there. Lisa has asked, I noticed in the new BBA product sheets that there are figures being quoted for Moulin burst strength and slip resistance. Are these important things to consider? Perhaps we could come to you for that one, Pam.
Yeah, sure. It kind of threw us as well, because obviously these figures historically, quite a few years ago, did feature in some certificates. They're not part of the European harmonised standards, so they've made they've not been in the certificates for quite a few years now, but they have been reintroduced in a number of updates, and it's really to do with not so much the performance during the lifetime of the building. It is very much based on the performance and the robustness of the membrane during the construction phase, which is as important, so you're not having to remediate or having inbuilt damage put into the roof before it's even slated. So, for example, the Moulin burst strength, that is a degree of how robust the membrane is and how likely it is to resist the loads associated with the installation of the roof. So, for example, most people have, you do have to preload the roof with the roof tiles, etc., during the process. And also you've got people working on there, and you've got tools, etc. So it's to do with that resistance of that additional loading during the construction phase. The higher the figure, obviously, the more robust and the more resistant that membrane is. Again, although it's to do with tools and resistance, it's not anything to do with personal safety. So it's really, really important to realise that these figures are purely for items going on the roof, not for humans. So you need to make sure you have your proper safety equipment, falls arrest plan, etc., risk assessments put in there. The slip resistance is kind of as it says, it's to do with a high coefficient of friction or lower coefficient of friction. So how slippy it is. So Proctor Air's got a really high coefficient of friction, which means it's got more resistance to items sliding off the roof. So again, that's things like putting your hammer down and missing a batten to catch it and it slides down the roof, or slate sliding down. So again, it's to do with personal safety behind or you know, for the people on the roof and below, etc. So again, it's nothing to do with, you know, it's not to see you can go dancing across your roof in the rain. It's nothing to do with that. It's purely for the items that are on the roof, not the personnel. So please always do your proper risk assessment and use your safety harnesses, etc., where appropriate.
Got it. Now, I've noticed that we seem to have lost Mark, so hopefully the team can work on getting him back on. He must have got a bit camera shy there. So Will, if I can come to you, please. Stacey's asked via email, I've heard that roofing membranes should only be used as temporary covering. Is this true, and how long can they be left exposed for?
That's a really good question. Yeah, it's true that they're deemed as a secondary waterproofing layer, which means although they will offer really good water resistance, they shouldn't sort of be left exposed for long periods of time. The idea would be to obviously get your roof covering on over the membrane as quickly as possible. Now, there's a couple of factors that you really want to take into account with regards to rainfall, how heavy that might be, and what sort of inclement weather might be coming in, but also sun UV degradation from sunlight as well. So there's kind of two key factors that come into play here. It's difficult to put a time on it because it can depend on the time of year, the location, how exposed it is, and also what's obviously that membrane currently protecting in your loft space as well. So our recommendation would be obviously to cover it up as quickly as possible. If it was the case that you knew that you had inclement weather coming in, say a heavy downpour, storms, that sort of thing, then you could potentially use a tarp as maybe a night joint just to protect the membrane and obviously the actual building beneath as well. So yeah, it's difficult to put an exact time on that answer, I'm afraid, but yeah, ideally see it as a secondary waterproofing that should be there if the main waterproofing layer, your slates or your tiles, were to become compromised, then it's going to do its job. But you wouldn't want to leave it exposed for, say, months on end, especially if you had sort of quite heavy downpours and inclement weather on its way.
Thank you very much indeed. That's absolutely great. Appreciate that one. Ian, I think I will bother you next, seeing as we're still missing Mark. Can Proctor Air be used with PV panels? This is a question from Alan.
We're getting some good questions today, Kira. PV panels, very topical, and something that we are looking at quite a lot, given the NHBC latest guidance on PV panels. It's caused a bit of confusion in the market where we're talking about permeable and impermeable roof coverings, and obviously majority of PV panels would fall into the impermeable roof coverings. With impermeable roof coverings, you should have an air gap below them and ventilated below that space to create air movement. With PV panels, it is also good to have air movement in that area for their efficiency. So it's quite topical. I've been dealing with NHBC and NFRC on this very subject because it's difficult to follow the BS 5250 guidance, because 5250 doesn't really talk about air permeable underlays. So for our underlay in particular, we're having to look at guidance for that in particular. So I've been speaking with PV panel manufacturers, speaking with roofers, house builders, and we do have guidance in our brochure. Personally, I think the guidance in our brochure, although I did sign it off, I think it's probably a bit onerous, and I don't think it's fail-safe with counterbattens, etc. But I don't think that's actually required. So I'm looking at coming up with new guidance on that, which will be an air gap, an adequate air gap, Now I've just got to define adequate.
Define what that is.
Yeah, if I can use the technical term depends, it'll be fine, but I don't think I'll get away with that. So I need to define adequate, and that's really where I am just now, and that's why I'm speaking with the PV panel manufacturers at the moment.
Good,
So
thanks.
it's a great question, a great one to start with, but please bear with us. We will have guidance with you soon.
Good, doing our due diligence. Ian, if I can stick with you, please. Graham has asked on the YouTube feed, are there conditions when the use of Proctor Air would require slate to be fixed to battens and not directly onto sarking boards per traditional Scottish detail?
It slates on the battens. There is circumstances where that could happen. In Scotland, it's quite alien because we like to put it into sarking boards. Maybe that's just a Scottish thing. But you can put it onto tile battens if you had the thermal insulation over the rafters. You would then put counter battens and then tile battens and fix your slates onto that. So there are circumstances where you could use tile battens, but if you're in Scotland, you might get some strange looks using battens with slate. That's not to say it's not right. You'll just get some strange looks.
Okay, good. Right, Pam, I'm going to come back to you in a minute, but first of all, I'm going to just give Will a question that we've had by email, if that's okay, from James Livingston. I need a roofing membrane suitable for an unvented between and under PIR insulated roof with no air gap batten and a counter batten and tiles over. What's the one to use? Is there any condensation risk? And can you do a condensation risk for me / building control? And will an inferior membrane produce a condensation risk?
Wow, there's a lot there.
Yeah.
So that was a warm pitch roof with the insulation between the joists, rafters, and underneath at roof line. And there's a counterbatten there, and the membrane, there's no air gap at all. So I assume they mean no air gap, no ventilation, or no sort of air gap for any moisture buildup and runoff there. So yeah, counterbatten roof. Our Proctor Air would be ideal for that. There's no reason why you wouldn't want to use that product there. There's obviously your counterbattens are going to create your channel for any moisture buildup on the outside of that roof, so to allow any buildup of moisture to escape easily out through the eaves. If there's a condensation risk, the only reason that would probably occur, I would answer that by saying probably not. It would be down to the insulation that's been specified, the thicknesses and the performance of which. So we would want to run a condensation risk analysis on that buildup. So get in touch with us, let us know exactly what insulation you're using and the thicknesses at each layer, and we can sort of do that for you and make sure there is no risk of condensation. It's probably unlikely because the chances are there's more between your rafter than there is underneath. But yeah, we can do that for you. What was the last bit of that question? Sorry, Kira.
The last bit of that question, let me just find it again. There's so many coming in, bear with me. Will an inferior membrane produce a condensation risk?
Yeah. Because there's no through ventilation from eave to ridge, I would say yes, that could happen on the basis that if you use something that wasn't allowing adequate passage of vapor and moisture, that could build up. So yes, there could be a risk in that instance. So you would want to make sure you're using a good quality air open membrane such as Proctor Air.
Okay, thank you, Will. I'm going to come to you, Pam, with another quite a long question, and then we'll start going through the YouTube feed and answering some of the reflections and the questions that are here. So I do like to do the email ones because people obviously take the time to send them in. So this is from Robert Moss. I had a scenario where I was asked to look at in a residential traditional re-roof with mid-span steel purlin, where a horizontal line of damp had occurred above the purlin, skimmed, and water dripped in below the purlin through a horizontal joint in the composite plasterboard. The construction was Romans on battens over a breathable 25mm air gap, 75mm PIR with 62.5mm composite plasterboard, fixed to the underside of the 100mm rafters. There was no rain at the time. It was icy with a small covering of snow. The water only came through on one side of the roof, not the opposite side where there were 3 Velux roof lights. Any ideas why or remedies? So a good cold bridging question here.
Yeah, and kind of the sort of thing that we're quite used to fielding in the technical team as well. So there's a few things obviously jump to initial mind. It's quite difficult because obviously we can't do sort of question and answer. So if you do want to give me a call, give me a shout later on. But first of all, your steel purlin, especially with insulation going between and below, although it's isolated from below, you've got basically a steel projecting outside. So ultimately that steel is going to be at similar, if not same temperature as the external environment. That then is validated. So I'm thinking possibly surface condensation forming on that exposed steel in that 25 mil ventilated void, or even if it's not ventilated, it's still going to be cold. So cold bridging, you were saying there's also, it was winter, that it was cold, it was icy, there was snow on the roof. So snow and ice on the roof can temporarily affect the ability for vapor to pass out of the roof. So if there's quite a lot of moisture passing through the roof construction, that can sort of back up a little bit. My guess is it was probably a northwest facing roof that really wasn't getting the sun very much. I'm also kind of guessing that there might be, one of the things to look at could be the placement and the installation of the PIR, PUR, the foam type insulation. So whilst that in itself is quite impermeable, if it's not fitted terribly well, you can get joints. So obviously thermal laminate plasterboards composites are really good, but you can't, you've got that sort of gap where they're put together. You could run a separate vapor control layer over the bottom and another layer of plasterboard, and that will help to control any vapor passing through, so you're not going to get bits, passing through onto the steel. We can also look at using things like space therm as cold bridge strip. That could be used to encapsulate the outside or just add a buffer to stop that condensation, because if it condenses, moisture condenses on that steel, it's going to take the path of least resistance and tracking down that passage of steel. So I think that's kind of where your moisture lines come in. I think the reason it's not happened, sorry, I did take a few notes. I think the reason it's not happening, says there was one side had Velux windows. There's a good possibility that those windows, just by nature of them being windows, are letting a little bit more heat and warmth escape from the building through that side. So it's just keeping that temperature of the steel higher than the other side without that. And also possibly the fact that it might be a south-facing roof as well. So yeah, it's just an unfortunate sort of reaction. You could have another winter where that never happens again, but there are some things that could be looked at to try and mitigate it. So if you need anything else, just, drop us an email to technical@proctorgroup.com or give me a phone and we can talk through it further.
Perfect. Thank you very much, Pam. Now, Ian, I'm going to come to you because there's a couple of questions here that I think we can cover with hopefully one answer from you around bats. So is there a vapor permeable roof felt that can be used when renovating somewhere with lots of bats? Natural England generally asks for one I felt. That's from Ben Tanner. And I'll just read out the other question that came through from Matthew. Could I ask the live team to respond on bat snagging and why Proctor haven't developed a snag-free option in their project range? I believe BatSafe, made by other companies, only available. Well, we don't like to comment on other products and other companies, but in terms of the Proctor side of it, I'm smiling because this is a bit of an ongoing project for us. Can you give us your comments on that, please, Ian?
Yeah, thanks for the question. Bats is something that we have looked at, and thanks for the get out, Kira, for allowing me not to speak about other manufacturers' claims. We have looked at this. We've had testing done. And we would love to tell you that our underlay is bat friendly. I think it's the terminology that people come up with. Unfortunately, I'm going to have to tell you that in my mind, what I felt, you don't hear me say this very often, is actually a good option if you've got bats in your roof or you have to take care of bats in your roof. The reason for that is that non-woven membranes are long continuous fibres, and the bats like to claw on the underside of the underlay and then snag on it and hang on the underlay, which obviously allows them to do that, but it also they get tangled up in it. From previous testing we've done, our membrane is less snaggy, which is, I don't know whether that's the right terminology, but means that the bats would take longer to snag on your underlay, but they would eventually snag on it. So unfortunately, I don't think at the moment there is a non-woven underlay without wires and things like that to try and stop them getting
And caught up in those fibers. And it's unfortunate because bats, they love these. They love the kind of roofs that the 1FLs will produce as well.
That's a very good point. I mean, I think certainly with our underlay, you get a nice dry roof, but that climate isn't great for bats. They like a kind of moist, more humid roof, which you don't get with an air permeable membrane, which is another problem. So we can't make the membrane less air permeable, but it's not the way we would like to go. So what I felt was a good answer in this particular case.
Okay, thank you, Ian. Well, Daniel has said on YouTube, I've often seen your bubbler demonstration, but I don't really understand exactly what this is showing me. Let's go to you to explain that one.
The bubble. I don't have a bubbler. Does anybody have a bubbler to show?
Technical have a bubbler.
You've got a bubbler. Yeah, it's you'd see
When
us,
I prepared earlier.
you'd see this at trade shows quite often, and when our guys are doing CPDs, they tend to take one with them as well. It's basically, as you can see, an acrylic tube. It's set sort of split into two chambers. The top chamber is separated by the bottom chamber with a membrane, in this instance Procter Air. The top chamber is filled with water, which sits on top of that membrane, and the bottom chamber has got a little pump where you can pump air into that bottom chamber, and you can see air bubbles coming through the membrane. So what that's a really good demonstration of is how air permeable a product like Procter Air is, but it's not allowing the water to pass down into that bottom chamber. So in this instance, keeping the roof watertight. If you were to replace that with a more airtight type membrane, you wouldn't see many, if any, bubbles coming through that membrane. So obviously the ventilation's not freely happening. So it's a really good demonstration to show that you've got air passing through the membrane, your ventilation's at a good level, but you've still got a watertight product as well.
Very well described. Thank you, Will. We should record that and send out to the sales team so they can remember how to describe it. Okay, so I'm going to come back to the YouTube feed here because I don't want to miss any. Sai has said, warm pitch roof detail. We've always used a minimum of 50 mil air gap above insulation. Now I note it's been reduced to 25 mil. Can you expand on that? So perhaps Pam or Ian could help Sai out with that question. Neither of them wants it. I'll pick one. Pam. Let's pick Pam.
Yeah, I mean, it's certainly with our air permeable underlays like the Procter Air, it's never been so much a case of needing an air gap. I think historically it was because the bitumen felts needed a clear void. It was just set at 50. I mean, Ian, I'm sure will correct me here or add extra context because he sat in a lot of the BS 5250 committees. But certainly with air permeable underlays, and to an extent in warm roofs with even just LR underlays, that zone is not really needed for anything too much. Maybe partial ventilation with an LR or full ventilation with an LR, but with an air permeable underlay, we don't need that void at all. It might be there for enhanced resistance for your insulation to enhance the thermal performance. But I think, just with sort of the developments and further reviews into how ventilation can be introduced into roof spaces, it may be that in some circumstances, depending on what you need to use, you can reduce it down to 25.
I think you're right. I could just add, yeah, good answer, I think. the 25 or 50 mil airspace is kind of historical, just exactly as you say, based on HR underlays that were being used. So there is that sort of theory that you need to have that airspace, but with the likes of our Proctor Air, you wouldn't need that airspace, and that's one of the advantages, that you can fully fill that rafter space without encroaching on the loft space or the attic area. So yeah, you don't need that airspace if you're certainly using an air permeable underlay. You might have to check if it's a vapor permeable one, if it's airtight, whether you need that, but certainly with an air permeable underlay, you wouldn't need that 25 or 50 mil space.
Thank you. Now, more reflection here from Peter. In your list of non-permeable outer layers, should you not also list man-made slates? So, any reflections on that? Did we miss that?
I think it's a good point. I worked on the British Standard when we were looking at different types of outer coverings, and natural slate. Obviously, the normal concrete tiles, clay tiles, interlocking were deemed to be air permeable enough and vapor permeable enough. Then the next test was natural slate, and because it's natural, there's lots of lumps and bumps, so there is enough permeability on it. So apologies if we missed that out, but it's a good point. We should have it in there. It's when it gets to sort of man-made slates where it's very flat, almost glass-like, that you can have issues of permeability and indeed capillary reaction there. But natural slate is fine, and a lot of our testing has been done with natural slate, obviously being a Scottish-based company.
Okay, good. And his other comment, just regarding the wind uplift, if a fixing specification in accordance with BS 5534 is obtained by the specifier from the manufacturer, the roof tiles should then be fixed adequately.
It's a very logical statement, and if they do follow the tile or slate manufacturer's fixing instructions, yeah, that is designed to stop slates getting blown off roofs. You do hear the comments of wind uplift and underlays creating problems. It's not a great one for me to comment on because I'm constantly battling people about that myth. I think in the old days when we used to fix every third course of tiles, I think that might have been more of an issue. But now with the new fixing regime, I think it's very difficult for a tile, for an underlay to actually flip off a tile in the prescribed manner. If you can do it in the lab, no problems, but in the real world, I've yet to see it as a real problem, unless it's not being fixed properly.
Yeah, absolutely. Thank you. Mel has said, I'm just trying to go down the YouTube feed here and catch up. Roof boarding, why is it required, and how do you deal with the barrier to ventilation? Pam, is that one for you, or Ian? Are you happy to take that?
I'm happy to take it just because I'm unmuted. So I'm muting myself quick enough. I'll run. So yeah, boarding. Sorry, was the question that do you need boarding or?
It was, why is the boarding required, and how do you deal with the barrier to ventilation?
Okay. Right, the boarding is not necessarily required. Again, it goes back to probably Scottish practices where we like to put softwood sacking boards on our roofs. That's more historical, going back to the times of where we've got water and sawmills and lots of wood in Scotland. So we can cut timber very efficiently because of the amount of water we have and the amount of sawmills. So it's a lot easier for us to make planks of wood than split laths, which is now called tile battens. So Scotland has always been historically sacking boards. again, for wind uplift, it helps, and racking strength. You don't necessarily need them. Even when you have sarking boards, NHBC will still ask you to put racking on the underside of the rafters. There's less and less of it being used, more slates in Scotland, but you don't need to have it. The more popular way for tiles, certainly in Scotland, is to use OSB or plywood, 8x4 planks. Now those sheet sarking, rather than boarded sarking, is a lot less permeable, vapor permeable or air permeable. So we would ask for, in those circumstances, with our underlay, that you ventilate the roof, because there's just not enough permeability due to the plywood or the OSB. With softwood sarking, you're very comfortable with it because, not least, it shrinks when it's got water covering on it.
You can also, just to add in, because Ian keeps telling us, tell them to turn it into a warm roof. If you're using like sheet sarking, like ply or OSB, if you did turn your roof into a warm roof, so place your insulation between the rafters, then that means that you don't need the additional ventilation that you do in a cold roof. So, you know, you can get the best of both worlds in that scenario and a usable loft space.
Very helpful indeed. Okay, Mustafa has asked around the differences between Roof Shield and Proctor Air. And as I say, on these webinars, we really like to keep the questions more technical, and we don't comment on other manufacturers' materials. However, if you want to email technical@proctorgroup.com or give us a call, we'd be happy to discuss Proctor Air with you and answer those questions. Okay, I'm coming back to a couple via email now. Will, if I can come to you, please. Gavin has asked, if I have insulation directly below an air permeable membrane, can they be in direct contact with each other?
Yes, they can. So the insulation obviously sitting below the membrane, and then the roof membrane over the top of that. Sometimes depending on what the buildup is. So if we have, I think we discussed this earlier, if we have a counterbatten system, the membrane could be in direct contact with the insulation. We just have to make sure that adequate either ventilation or a zone is created to allow any moisture buildup to easily flow out of that roof. So this can be created in a non-counterbattened buildup with a drape in the membrane. Although there's no exact requirement for the minimum drape, sort of between 5 to 15 mil would be ideal. So that's going to create that enough of a channel for any moisture buildup to flow underneath the horizontal tile battens, and therefore not create any buildup of moisture, which could damage those tile battens. It's an easy test for this as well. If you're not sure, get a cup of water and pour it down those channels and see if it flows straight through. It's nice and simple. But yeah, there's no real reason why it can't be in contact if it's a vapor permeable membrane.
Okay, thank you, Will. And I have another one here from Josh. We seem to be having longer periods of wet weather, perhaps as a result of climate change. What steps have been taken to mitigate this with Proctor Air?
Okay, yeah, it is a very good question. We do seem to be having heavier downpours. I think that's kind of been reported on, that although we might not be getting more over the course of a year, we're certainly getting more intense storms and downpours, which can be causing issues and risks. Potential risk to leaks. We mentioned earlier about not leaving membranes exposed for too long a periods, or if we know there's going to be inclement weather coming in to play. Proctor Air actually is a good example of what we have done to sort of improve the product, is making sure that we do have like hydrophobic content in each layer build up of the Proctor Air. And what that does is it really helps to repel any surface moisture and water that's fallen onto the membrane, and should really prevent that passing through that membrane. Not just on the first layer, but the second and the third layer of that membrane as well has that hydrophobic property additive, which really does improve its performance. And we have seen already where the membrane has been left exposed in quite severe conditions in the southwest, where it's quite a high exposure zone. It's fared very, very well in these conditions and helped to sort of push away any moisture that's sort of been directly in contact with that membrane when it's been left exposed. So that's the one thing I can think of off the top of my head. I hope that answers that question.
Yep, good. Anything to add, Pam or Ian? No? Excellent. Ian, James has asked, can underlays be affected by timber treatments in the battens?
We're getting the real topical ones today.
I know, right? Nowhere to hide.
It's like an exam. Yeah, it's a good question. Again, probably topical as well. There has been claims made on timber treatments affecting underlays, but that's not new. In the old days, they used to call it surfactants problems.
Say that again, sorry. Say that again. Used to call it
Surfactants, and it breaks down the surface tension of the underlay, and some underlays rely on the surface tension in adding to the water resistance of the product. I was at a meeting recently where a guy who'd been in the industry for a while had actually asked, what is surfactants? They thought it was a Scottish term. But no, it's probably about 10 years ago, 15 years ago, it was talked about quite a lot. Not so much now. But timber treatment, without using the technical term, it all depends. It's a word we like to use in technical because you don't know what the timber treatment is. So it depends on what the timber treatment is, whether it's water-based or solvent-based, and what type of treatment there is in that. Now, the timber treatment has become, certainly in tile battens, a lot more regulated with BS 5534, slating and tiling regulations, code of practice, which makes it more difficult to come up with timber battens that have all different types of timber treatment. In the old days, it might be creosote and things like that, and puppy dogs' tails. But nowadays, they're much more regulated. And we're doing testing with timber treatments at the moment, where we're taking the tile battens, submerging it in water, and using the residue water in Will's bubbler and testing it like the W1 test to see whether it will affect the water holdout. So far, we've tested 3 different timber battens, and it's all resistant to the Proctor Air material. So we will be putting out a press release on that soon, so watch this space.
Good. I'm going to skip right to the last question we've had, because it sounds urgent, from Andy. Good morning, please help. So just in case he has anywhere to go, I'll come to you for this one, Will, please. Cold roof, Proctor breather chosen, fibre slates. Do I need a counter batten or not, please?
Okay, so under fibre slates, we'd always want to look at a ventilation, cross ventilation from eaves to ridge. So it will depend on the rest of your build up. If you can't provide that ventilation in the rafter space, then yes, counterbattens would be needed. But if you can sort of get in contact with your exact build up, then we can have a look at that for you, run the condensation risk analysis, and yeah, make sure we get the correct and sort of answer to you there.
Yeah, if in doubt, send the drawings and we will look at, absolutely. Pam, I've got 2 here via email from Andy Frew, and as I say, I do like to do the email ones because people take the time to send them. We may be replacing the roofing felt at roof eaves to re-insulate there from above. What would be the effect of replacing old felt with a breathable felt at this point? A breathable membrane, I should say.
Yeah, okay. So another one of Ian's favourite sayings is not all membranes are created equal. So things like if you not all breather membranes have got the same performance. So you kind of have to consider if you mix and match them, you do have to look at what is the lowest common denominators, which is the more onerous consideration there. So you've still got your bitumen felt. So that's not to say that if you're having to do remediation at the eaves, that it's not a good idea to future-proof your roof by replacing the bitumen felt with, say, a strip of Proctor Air. But you've got to remember that that section may not necessarily provide enough ventilation to the rest of the roof to be able to negate the requirement for your ventilation. Now, hopefully, if you've still got 1FL on the roof, you will have a ventilation path there. So by including the Proctor, you're not disturbing that or affecting it. You shouldn't be making anything worse. But you're also starting to future-proof your roof. And if you then have to or want to go in and do further work further up the roof, then you can obviously continue that membrane over the top of the roof. So I hope that kind of answers it. It doesn't replace the need for vents, but it won't make it any worse.
Okay, good. Very honest and technical answer. Thank you, Pam. His second question was, do you make roofing membranes with a heat reflective underside? Could these be added below rafters on the south side to resist solar overheating or frost in the loft?
It's a good question. Radiant barriers are used a lot in hotter climates like Australia and that, where obviously radiated heat is a huge, huge issue. But they're more sort of cooling climates than heating climates. I'm not sure how effective they would be in a cold roof like in the winter, to resist frost. I think there you've got better ways of reducing that risk by ensuring that you're controlling the moisture passing through your ceiling, that you're closing off the tops of your cavity walls to stop excess vapor getting in there, making sure you ventilate your building properly with extract fans, and considering something like an air permeable underlay to make sure that you effectively reduce the amount of vapor in that roof space, so making it a drier place. And unless you're in some of the really extremely exposed places of Scotland, I think the risk of continual or excessive frost are probably relatively limited. It's not like it's going to be lasting for months on time. It's certainly been a long time since we've had sort of like those really sub-zero long-term temperatures. It's not to say they're not going to come. One of the big problems about heat reflective ones is they generally have metallized films, and they can affect the permeability. So it might be that you have to then perforate it, which affects the water holdout. So there's lots of reasons why it may not be functionally suitable, in terms of it might compromise the roofing membrane and mean that your roofing membrane doesn't meet the requirements of the harmonized standards in terms of water holdout and permeability. In terms of overheating, it's a possibility. You'd have to obviously make sure that you've got a ventilated void. You could look at something like a reflective thermos, a vapor control layer, however. So install that on your ceiling on the underside of your rafters, put in a service zone, really great for your air tightness, running your cabling, etc. And that might help, keep the rooms a bit cooler. But yeah, it is a difficult one. And probably something that's going to come more to the fore.
Yeah. Well, coming back to that, actually, we had a good question again by email. Let me find this from Rob Jones regarding overheating. So if I come to that, you for this one, Ian. It's really good. I love getting all these questions. It's just trying to make sure we get to them all. Bear with me 1 second. Can't find it. Bear with me. Oh, here we go. Okay, so Rob Warren had said, as overheating is likely to become a bigger issue for houses, does wind washing on a hot summer's day mean that room and roof conversions are more likely to overheat if they have gaps in the insulation layer? Insulation is supposed to keep you warm in the winter and cool in the summer, but it seems that thermal bypass and wind washing can limit the effectiveness of both.
I think Rob is a regular on the webinars, and I think I've possibly answered similar questions to him before. Yeah, overheating. Probably about 15 years ago, I was in a British Standard in London, and somebody told me that there could be a problem with overheating in the UK. And at that time, I didn't believe that was going to be an issue. I reckoned anywhere south of Birmingham was going to spend more money on cooling than heating. And obviously, having just travelled down from Scotland, I thought this was quite a crazy idea. However, yeah, overheating is definitely an issue now, especially with air tightness in buildings. We don't have the nice chimneys that we used to have. So yeah, overheating is a potential risk. To go back to Rob's question about wind washing. I'm looking at my colleagues there. They probably all know my views on wind washing, which is potentially an issue. But again, to go back to a technical term, it depends. Depends on what the construction is and whether air can get through that and what effect it would have and what type of insulation it would have, what the membranes are used. All very much a build-up. Now, again, going back to Rob's question, he's mentioning air tightness in the insulation. Now, that's really an important part. Put the insulation in tight between the rafters, tight between the studs. It is an important part, and sealing that. So it's well worth considering that. So if there's any particular worries on a particular project, we'd love to look at it and look at the various parameters there and see whether there is a problem or not.
Good. Okay, I'm darting back to the YouTube feed here because I don't want to miss any. Question here, Will, if I'll come to you, please. S14W897 has said, question, when we have a cold roof with OSB ply as a sheathing, where should we ventilate? Below the sheathing or above or both, depending on the covering?
Okay, so if we've got a cold roof, the chances are that underside of that OSB and sheathing board are going to be cold. So we'd expect to see a risk of condensation there. And therefore, you would expect, you wouldn't expect, you would need to alleviate any risk of condensation. In my opinion, yes, you'd want to ventilate underneath the timber sheathing board. There could be an argument to say if we've got it open jointed enough, you might be able to alleviate that, but I'm not too sure why you'd do that in that circumstance. And also, you're really depending on level of workmanship in that instance. Yeah, keeping it simple, I'd say ventilate underneath the timber sheathing board.
Okay, wonderful. Thank you very much. Pam, back to email. I'm sorry, I've had one here from Joe McGuigan. I'm not sure, sorry. I was wondering about vapor permeable underlays. I believe it's important to have some form of ventilation below this. For example, a build-up comprising vapor control layer, so optional vapor control layer and plasterboard, if room and roof, rigid insulation, foil backed between the rafters, sarking, just to clarify, the sarking would be 2-3 gap boards, roof shield or Proctor air, so we'll concentrate on the Proctor air, please, and slates. Would the membrane serve little purpose as the insulation is hard against the underside of the sarking, especially if it's foil backed? The rafters would also receive little ventilation. And he said, hopefully we can fit this into the Zoom call.
Yeah, no problem. Again, this is one of those ones, if you want to go into it in more depth, more than happy to discuss it with you. If you're having insulation sort of warm roof from the roof, some sort of vapor control is always good. That very often can be done with your foil-backed foam insulations because they are by their very nature more resistant than mineral wool. You have got movement of the vapor through the sarking gap. So what we're looking at here is more vapor movement rather than ventilation. So by using permeable products like your insulation, sorry, your sarking boards that have got the gaps, so vapor can pass through those gaps, can pass through, albeit more slowly, through the timber as well. And by using Proctor air on the outside, that's not stopping, that's not inhibiting the movement of that vapor. So another phrase we use quite a lot, especially with our wrap tight, is moisture neutral, vapor neutral. That membrane is not impeding the ability for that to dry out and that vapor to pass to the outside to where it's not harmful. So generally you don't need, it's not that the membrane serves little purpose. The membrane's there really in that scenario to not make the situation worse, or in the case of air permeable ones, help, but also to provide that secondary moisture backup from ingress of wind and rain driven snow up through the slate joints and things like that. So it's kind of a twofold function. So I mean, the membranes are important, but by using an air permeable, it means that you don't have to have any consideration, especially in a hybrid room and roof. In a lot of situations, they come in under sort of cold roof certificates, so you have to do partial ventilation or drop the insulation. By using an air permeable like Proctor Air, it means that you don't have to worry about any additional ventilation. You can just sort of, go on and fully fill your rafters where you want to and not worry about anything like that.
Kind of like a fail-safe option, if you like.
Absolutely. Your future, I use the word future-proofing. You're future-proofing your roof against, potential problems.
Yeah, good comment. Ian, this question here is a bit of an extension around the timber treatment one. So the question was, have your membranes suffered of late due to recent regulation changes to PTFE, PFAS? I've had more problems of late from water getting through membrane before tiling.
Yeah, I think, excuse my lack of knowledge of the acronyms, but I think that is dealing with the timber treatment. And I've read that and wondered whether it was of late or whether they were talking about the lofts. But yeah, you're right, it's late. Yeah, there has been problems. We've heard of lots of problems with, not lots of problems, but problems with timber treatments affecting underlays in the water ingress. As I said earlier, we are doing testing to show whether that is a problem or not. So far, that's not been a problem from our testing.
Good. And Ian Stewart, another one for you here. Dirt, moss, and algae can build up between overlapping roof components and reduce long-term permeability. Is roof maintenance or cleaning required to control this? He's asked.
Yeah, it's a good question, and it's one that's been raised with vapor permeable and air permeable membranes for at least 25 years, that these membranes will clog up with dirt and dust. Indeed, BBA actually did some testing on roof and underlays where they poured dust on top of the membrane to check whether it would have any effect on the permeability. And it didn't have any effect on the permeability, or the membrane still continued to breathe and vapor permeable because of the molecular size of dust compared to the molecular size of the underlay and allowing that vapor to pass through it. In terms of tiles, you should probably have regular maintenance of that. I'm hesitant because I'm not wanting to tell people to necessarily power hose the tiles, but be careful what you do. But a brush of the tiles would be sensible.
Okay. Mel's commented here, when using interlocking tiles, is it necessary to ventilate the space under the tiles even with the use of an air permeable membrane? And the same question goes to if using metal roofing. Pam's nodding there. Do you want to take that one?
Yeah, I can do. So this is follows on from the fibre cement slates that we were looking at, talking about metal sheet tiles. A lot of these products have got, they're not the sort of small discontinuous roofing of of traditional slates. So usually things like clay tiles, natural slates, even concrete interlocking tiles, they're all deemed to have enough irregularities and gaps around them to be air permeable. So there is guidance in both 5534 and 5250 over what that air permeability figure should be, and also how effective how to test that. They're basically, with things like metal tiles, metal sheets, close-fitting man-made fibre cement slates, assume they're impermeable, therefore you have to ventilate the batten cavity. With things like interlocking concrete tiles, they're probably permeable enough, so you don't need to consider any additional ones, any additional ventilation. But if in doubt, check with the tile manufacturer. They should know whether their system is deemed air permeable sufficiently or not.
Got it. That's perfect. Now we've had a good question in from David at Kier Construction, but it's quite a long one. So what I'm going to ask the team to do is just post it on the YouTube feed, so the team, the panel can read it, and also the individuals, because it's quite an interesting question. So if you guys can do that, hopefully they're listening, and then we'll come back to that question. So I think we probably have about 5 questions left. I'm just trying to work my way through the outstanding ones. So if you want to stick with us, please do. If you have somewhere to be, then don't worry, you can always come back and catch up at a later time. So Will, what about rodents eating the membrane? Delphine has asked.
Okay. Membranes, our specific membranes, they're not going to sort of hold any food value for rodents. Obviously, rats and mice. It's probably a bit of an issue if rodents can actually get to the membrane. There is guidance given in both 5250 and 5534 about preventing this from happening and minimizing any sort of openings and gaps that are being left during construction. And when it's finished, I'm not 100% sure of the actual dimensions, but I think it's pretty small, sort of less than 5 mil. So that's probably your bigger issue, because they are going to like to get into a loft space where it's warm. They've got things like fluffy insulation and stuff that's probably been left up in the attic that they can bed in. And so from a food source, there's no real risk, but that's not going to stop a rat from tearing up a membrane and using it for bedding, for instance. So you want to try and limit any sort of risk of them entering into that loft space in the first place.
Good. I mean, Pam, in all your years with Procter, how many times have we had an issue with rodents eating membranes?
Sometimes rodents, sometimes is it a question, is it even things like wasps, because they can eat through to expand their nest. It's not that they want to eat the membrane, it's just to expand through the membrane to grow their wasp spikes. But yeah, I think maybe 2 to 3 times tops have I had something where it looks like a rodent has nibbled it, and it's quite obvious. It's like little crescents. Sorry, having owned gerbils in the past, you kind of know that kind of rodent sort of nibble round. It's like little crescent moons, and it's quite obviously nibbled. It's quite obviously chewed, but there's not as
very often.
Yeah, no.
Millions and millions of square meters sold and 2 to 3 issues. So, but I mean, it's an interesting question. So it's good.
Absolutely.
Now we've had that very long question posted on the YouTube feed. Again, Pam, is that one that you'd be able to comment on?
Yeah, I've kind of been having a read through it. So just sort of recap: impermeable roofing underlay, ventilation, quantity of condensate, so mold and everything starting, which is obviously not great. So that to me either indicates that the ventilation may be blocked up at the eaves. So sometimes that can be quite difficult to achieve with the amount of insulation we're having to put in. Could there be additional moisture coming into the roof space through like maybe the tops of the walls not being capped off? Could there actually be cold moisture being dragged into the roof through the ventilation? But there's obviously something going on there. It's kind of a difficult one to know, because it's trying to identify what's causing that moisture overload in the first place. And that might need to be looked at, how old's the building? Has there been anything else changed within the building? So have you put in different windows, different doors, different occupancy use? Because all of these can change the building physics. It is right. I mean, 5250 does sort of state that if the ventilation is there correctly and maintained, it should provide enough for protecting that roof. Is it a new roof? Sorry, I'm just kind of thinking my feet here. Is it a new roof? Could it be the drying out period?
So we're watching a live Pam trying to work her
trying to work it through. I know, exactly. So there's a few things that could be going on. So certainly using, like, having a vapor control layer, you don't always have to use that in a cold roof, but it does stop the vapor getting into that roof space. So it stops the vapor from the dwelling areas overloading that roof. Depending on how well things like vents and fans and ceiling lights are installed, how well the loft hatch is installed. So have you got a well-sealed ceiling? that could be contributing to an overload. You could be looking at needing to revisit, maybe retrofitting a vapor control layer or foil black plasterboard below to try and mitigate the amount of vapor that can pass into the roof. Obviously, worst case scenario, you might have to re-roof it with something like Proctor Air to help sort of mitigate some of those issues. And certainly our cold roof BB product sheet does state that you don't have to use a vapor control layer is not needed. It's
jump in there, Pam.
yeah.
I think there's a lot of good questions in there. If I could start with on the project where it's ventilated, it's quite interesting that I was involved in the PII research, I think showing my age, back in the 2000s, where there was issues with ventilation of cold pitch roofs. Not always, a lot of it works really well, but there was projects where there was condensation. So what they did was they put ventilation in, and there was still condensation. So they put more ventilation in, and it just increased. That the more ventilation they put in, the more condensation. It never solved the problem. And the PII project went to Europe, and I remember a professor in Belgium saying, that's a problem with the UK. If you've got a problem with moisture in your loft, you ventilate. If you've still got a problem, you ventilate more. You don't actually think about holistically what the problem is. And I think with this particular project, you should think about it in all roofs, but you want to think about it holistically. Why is there a problem in this roof? Is the residents performing as you would expect them to? And most often they're not. They might have small children. Kira, you'll be able to tell us that small children create lots of vapor, not them personally, but bathing, and you're spending more time in the house, so there is more moisture load with a smaller family. So it all depends on a lot of factors, and you have to take that into consideration, almost like a checklist of questions. Have you done this? Do you do this? Do you do this? We've actually put monitors in lofts and in the house previous to try and identify what the issues are. And we've got identical rooms, identical buildings, and one problem, there was a moisture problem, and the next to it never had any moisture problem. Now, that was something as simple as the one that didn't have any problems had their windows open for a long period of time so the vapor could escape. The one that did have the moisture problems kept the windows shut. So I think we'd have to look at it holistically as to what the problem is there. I'm pretty sure we could come up with a solution, and if re-roofing's not off the books, then that's a good potential options as well.
I mean, it's a whole other webinar probably, but it's interesting what you said about the moisture. There were no issues when the windows were open and issues when the windows were not open. And I think it's probably something we should do at some point, talking about the role of sort of education of inhabitants of these buildings is so important now, especially with air tightness. But we'll talk about that another day. I just find it really interesting in terms of the behaviours of the individuals within that building and how that then can affect the performance or cause issues, which is quite interesting. Anyway, moving on. I think I have 3 questions left. So let me just find them. One that was quite far back. So Ian had asked, should I consider specific methods for steel sheet roof design for domestic property with an air vapor permeable underlay, direct non-ventilated cold pitch roof void, ceiling mineral wool insulated and high level airtight and AVCL at ceiling level? So Pam, we've not heard from you for a wee while. Is that one you can help with? But you're on mute, Pam.
Yeah, so the metal sheet roofing obviously is your kind of sort of your lowest common denominator there. So it may be that does require some ventilation. Sorry, I'm just going to try and find that again in the feed just to remind me what was in it.
It's quite near the top. Sorry, I seem to have missed it.
No, it's fine. I will zoom up. Yeah. Just so that I address everything. Right. Trying this one. Sorry, I've got 2 or 3 things running with all the questions on, so I can.
That's the joys of live question answer. At least these are real questions that we actually have to think about and answer, you know?
I know. Yes, so I think in a lot of situations, some of the metal sheet roofing, standing seam roofing, things like that, is considered permeable by the manufacturers because there are some, there is the ability for that sort of like the way it sort of curls round, it does allow vapor to track out. I think a lot depends on the placement. So if it's a cold roof, you probably would need to consider that as a ventilated roof space. If it's a warm roof, it's obviously less critical. So yeah, I would probably sort of say, probably just sort of drop us an email and let us see the drawings and the plans, and we can give you a little bit more tailored advice.
Okay, good. Well, a very quick one here for you, please. Peter O'Donnell, does the glue in Raptite have an adverse effect on the permeability of the membrane?
Okay. Raptite can be used in pitched roofs actually, if you're looking for an airtight, if you've got an airtightness strategy. So it's quite nice that's been brought up. The adhesive that's used on the back of Raptite, which for those who may not be familiar, is a fully adhered membrane, so that'll get stuck back to a continuous substrate, maybe in pitched roof like an OSB sheathing board on the outside. It's been tested for its vapor permeability suitability with the adhesive in it. So although if you took the base membrane, tested that separately to the adhesive, there may be a difference. The vapor permeability of Raptite is 100% suitable for its application, either in roofs or walls. So yeah, absolutely fine. The adhesive is not going to certainly have any sort of detrimental effect on that vapor permeability because it's tried and tested.
Good, thank you very much. Okay, so our last few questions. Ian, John Orchard Associates have asked on YouTube feed, with a hybrid loft conversion and an existing HR underlay, what recommended ventilation should be allowed at eaves and at high level?
Yeah, and HR underlays, without sounding like a cop-out, is not our bag at Proctor's. So we would advise you to follow BS 5250 in that case, with eaves and ridge ventilation. Assuming it's a cold roof, it's a warm roof, you still have to ventilate below that space with either high-level ventilation or ridge ventilation along with eaves ventilation.
Okay.
But, we can't really be more specific than that.
Okay, good. And Zajan, just while you're unmuted, Ian, seeing as you're happy to answer another one last time, standing seam is supported on profiled metal liner. Does it require a certain breather membrane in between, like you would when supported on an OSB board?
Yeah, the standing seam, certainly the ones I've seen on the standing seam, they've got halters that obviously the standing seam clicks into. And I've seen breather membranes used with a standing seam, and it's not particularly successful if we put it on top of the insulation. So we've got the halters fixed into the sheathing board, then insulation, then they try and put the breather membrane on top before they put the sheet on, which is not particularly successful because you have to cut round every one of the halters. The best way would be to put an underlay below the sheet to create not so much as a breather membrane, but more as a slip plane to allow the membrane to move in that particular circumstance. Obviously, with a metal sheet sitting on top of it, it doesn't change the permeability, so it doesn't make the sheet permeable. So a lot of the benefits of the permeability you wouldn't get, but the breather membrane could act as a slip sheet in that circumstance.
Okay, good. Right, I am down to my second last question. So Ian, I'm going to stick with you for this second last one. How important is air permeability, and is higher better?
Oh, that's another good question.
They're challenging today. They're challenging today.
You give me the good ones today. Yeah, air permeability. Obviously, we're going to say it's important. How important? Again, we'd probably say very, especially in cold pitch roofs. Is it better for the air? A better, higher air permeability? Is it better? That's the question, and it's one that certainly Pam and I will have discussed in the small hours, probably over a drink, as to whether it is better or not. I think there is some manufacturers claiming higher air permeabilities that's best. I think by the same token, having a low air permeability is probably two extremes. I think there's a sweet spot in the middle. With all membranes, you should be looking at vapor permeability, air permeability, water resistance, and whatever you change in one, you're likely to have an effect on another. So I think there's a sweet spot which seems to be around about 30 to 40 in terms of air permeability, meters cubed per square meter per hour at 50 pascals. Now, our membrane is a nominal over 35, but it's designed that way. We don't want to have 70 air permeability, because if you have more air permeability, you've got a risk of more water penetration potential. But you definitely have the risk of it becoming more like a net and not being able to take the wind loads that it's designed to take when the wind hits that roof. So I don't think higher is the better. I think there's a sweet spot. Probably no surprise that I'll tell you that it's between 30 and 40, and that's where our membrane is. But it's designed for that particular purpose. So hopefully that answers the question.
Yeah, I like that kind of holistic approach. You have to look at the entire performance of the membrane rather than just saying this figure is better than that figure. But we're very happy with where our figure is, I would like to add. Okay, this is a question I missed earlier, and Will, I've not spoken to you for a while, so I'm just going to come to you. No reason why it's the last question, just happens to be the last one, unless anyone wants to post anything else. So Timothy Crone had asked on the YouTube feed, SIPS roof construction. I know you don't go into detail how to ventilate above a SIPS roof. Is there a separate CPD relating to this type of construction?
No, there's not a separate CPD as such. It's probably a relatively straightforward answer. So a SIP, structurally insulated panel, they do come in different guises, but traditionally a layer of OSB either side of a sort of chunk of insulation to determine thickness to achieve a particular U value. So it's in essence like a sandwich panel, OSB either side of insulation. The majority of the time they're not ventilated. You sort of deemed a warm roof system, so you'd have your SIP, and then above that you'd have your membrane, and then you would need a counterbatten because obviously it's a fully taut membrane there, so you would need a counterbatten running from eave to ridge, sort of 25mm minimum, and then your cross battens and slates or tiles. However, we've mentioned earlier about impermeable tile coverings, and if there was a roof covering that needed ventilation, then you would simply look to bump up that counterbatten to say 50mm, and then you'd look to introduce cross ventilation at eaves to ridge as you would do traditionally. So it does solely depend on the external finish, but the majority of the time it's quite a modern method sort of building a house. So you would look to just to go with the unvented system would probably be the most traditional.
Okay, thank you very much indeed. So we'll end on that. Unfortunately, we lost Mark Blackie, who is, really knows his stuff on all things roofing and membranes and all sorts. So I'm really sorry that we lost him today. And well done to you three chaps and ladies for answering the questions there, because that was some really challenging, good questions coming in from the audience. So I'd like to thank our viewers for not just attending, but providing these challenging questions, because they're hard to answer last minute. And it really gets, the juices flowing and us thinking about what the market and what the industry is looking for clarity on. So it's extremely helpful. So thank you very much for attending. And for those of you that stayed on this long, I hope you find it beneficial. Thanks again to the team here on screen and the team off screen who worked really hard putting these together. You will have access to your CPD certificate on our webinar page, which is www.proctorgroup.com/webinar. And keep an eye on that page and you'll be able to register for our next webinar, which is generally probably in 1 to 2 months, depending how quickly the team can get around to putting it together, because there's a lot of work in that. If you want to book a meeting with one of our team, request information on the products we've discussed today, you can do this. You can request that on the same page. Don't forget about our Proctor podcast that we launched a couple of weeks ago. As I say, it's around all things modular construction, the first one. And it features Will Jones and also Adam Salt, who heads up the modular division of the business. And it's quite interesting talking about where it's come from, where they see it going in the future. So please have a listen on one of the various platforms you can find it on. I think that's it. If you enjoyed today, please give us a thumbs up and subscribe to our channel if you want to be made aware of anything that's forthcoming. Thanks for your support, and we hope to see you again in the future. Thanks, guys.